cubic equations and the conjugate roots theorem. A complex cubic polynomial is one of the form f of z is equal to az cubed plus bz squared plus cz plus d, where a, b, c and d and z are elements of the complex number set. The factor theorem applies to complex cubic polynomials just as it does to real cubic polynomials. Thus, z minus z1 is a factor of f of z if f of z1 is equal to 0. We can also use long division to verify that z minus z1 is a factor of f of z. If we have one root of a complex cubic, we can use the factor theorem to solve the cubic equation. Example: p of z is equal to z cubed minus 3 plus iz squared plus 2 plus 3iz minus 2i, where I squared is equal to minus 1. Part 1. Show that p of I is equal to 0. So we have the equation z cubed minus 3 plus I z squared plus 3 plus 2iz minus 2i. So since this represents p of z, if we want p of I, we need to swap each z, substitute each z for I. So p of I is going to be I cubed minus 3 plus I times I squared plus 2 plus 3i times I minus 2i. So we basically just swapped each of these z's for I. And now we expand. So I to the power 3 can be broken down as I squared times I to the power 1, because 2 plus 1 is 3. I squared we know is minus 1. Make sure there's brackets around it. And 3i times I is 3i squared, and 2 times I is 2i, and then we just have our minus 2i. So I squared is minus 1, and minus 1 times I is minus 1i. And I squared is minus 1, so we'll have 3 multiplied by minus 1. Minus 1 by I is minus I. And we still have minus 3 plus I times minus 1. We still have our plus 2i, and 3 times minus 1 is minus 3, and we still have the minus 2i. Now, the minus in front of the 3 plus I is going to be multiplied by the minus 1 to give a plus. And likewise for the I. So we end up with minus I plus 3 plus I plus 2i minus 3 minus 2i. We put the real parts together, so we've 3 and minus 3, and they will cancel. Then we put the imaginary parts together, so we've minus I plus 2i minus 2i. They will cancel and they will cancel, so ultimately we're left with 0. So p of I is equal to 0. Part 2. Solve the equation p of z is equal to 0. So by the factor theorem, z minus I is a factor of p of z. This is because p of I is equal to 0. So if p of I is equal to 0, then z minus I must be a factor. So we set up our bus stop, and we have our equation for p of z underneath the bus stop, and we have z minus I outside the bus stop. So z goes into z cubed and leaves us with z squared. So over here we're going to do our rough work. So z squared times z minus I will give us z cubed minus iz squared. And we multiplied z squared by z minus I because z minus I is what's outside our bus stop. So we're going to write the z cubed minus iz squared underneath the bus stop. Now the z cubes will cancel. The minus iz squared and the minus iz squared will cancel as well. And we're left with minus 3z squared. So we bring that down here. And then we repeat the process. So z divides into minus 3z squared and leaves us with minus 3z. So we go back to our rough work. Minus 3z times z minus I is minus 3z squared plus 3iz. And we write this down underneath our bus stop. So the minus 3z squared cancel. The 3iz and the 3iz cancel. And we're left with 2 multiplied by z, which is 2z. And again, we repeat the process. So z into 2z goes twice. So in our rough work, 2 times z minus I is 2z minus 2i. So we write this down underneath our bus stop. And the 2z's cancel, and the minus 2i's cancel, and we're left with 0. So z minus I divides into our z cubed expression and leaves us with z squared minus 3z plus 2. So this is one factor of our expression and this is the other factor. The other factor is z squared minus 3z plus 2, and the equation can be written as z minus I multiplied by z squared minus 3z plus 2 is equal to 0. Or we can factorize this, which will give us z minus 1 times z minus 2. So if z minus I is equal to 0, then z is equal to I. If z minus 1 is equal to 0, then z is equal to positive 1. And if z minus 2 is equal to 0, then z is equal to 2. So our solutions are I, 1 and 2. A theorem that can help us to solve some, but not all, cubic equations is the so-called conjugate roots theorem. So here we have the conjugate roots theorem. If f of z is equal to 0, is an equation with real coefficients, and if z1 is a solution of this equation, i.e. f of z1 is equal to 0, then the conjugate of z1, z1 with a bar on top, is also a root of this equation, i.e. f of the conjugate of z1 is equal to 0. It is very important to be aware that the conjugate roots theorem can only be used if all the coefficients are real numbers. For example, the coefficients in the equation z cubed minus z squared minus 7z plus 15 equals 0 are all real. 2 plus I is a root of this equation. Then the conjugate roots theorem tells us that its conjugate, 2 minus I, is also a root. However, the coefficients in the equation z cubed minus 1 plus I z squared minus 4z plus 4 plus 4i equal to 0 are not all real. So, for example, minus 1 plus I and 4 plus 4i are not real, so they have imaginary parts in them. The conjugate roots theorem does not apply to this equation. 1 plus I is a root of this equation, but it is completely false to say that its conjugate, 1 minus I, is another root. Find the values of the real numbers a and b if 2 minus 3i is a root of the equation z cubed plus az squared plus bz minus 65 equals to 0. Find the other roots of this equation. So 2 minus 3i is a root, and by the conjugate roots theorem, 2 plus 3i is also a root. So this is the conjugate of the first root. Thus, a quadratic factor is z squared minus the sum of the z's plus the product. So we know from algebra that if we had the roots of an equation to be 3 and 2, that would mean the factors are x minus 3 and x minus 2. If we multiplied out these brackets, we would end up with x squared minus 5x plus 6. So we can see that the coefficient of x is minus 5, which is the sum of the roots. So minus 3 minus 2 is minus 5. And that the constant at the end is a product of the roots. So minus 3 times minus 2 is positive 6. So we can use this idea with complex numbers. so that the sum of the roots will give us the coefficient of, in this case it will be the z, not the x, and the product of the roots will give us the constant at the end. And instead of x squared, we'll have z squared. So z squared will be minus the sum of the roots plus the product of the roots. So the sum of the roots will be 2 minus 3i plus 2 plus 3i. So we have 2 minus 3i is our root and 2 plus 3i is our conjugate. And then the product of the roots will be 2 minus 3i multiplied by 2 plus 3i. So we bring down the z squared. We have 2 plus 2, which is 4. And we have a minus in front, so we've got the minus 4. And then we have minus 3i plus 3i will cancel. So that minus 4 is now stuck onto a z. And then multiplying out 2 minus 3i by its conjugate, the quick way to multiply conjugates is we square the first number, which is 2. We square the second number, which is minus 3 or positive 3. And either of those squared is 9. And then we add to get 13. So now we have a quadratic factor of our equation. So we're trying to find the other roots. So like we did in the last example, we can divide the root, which we've just worked out, into the expression that we have. So we're going to set up our bus stop. So we have z cubed plus az squared plus bz minus 65 under the bus stop. And we have z squared minus 4z plus 13 in front of the bus stop. So we're going to divide z cubed by z squared to get z. And then we're going to do our rough work. We're going to multiply z by z squared minus 4z plus 13. And multiplying that out, we get z cubed minus 4z squared plus 13z, which we write underneath the bus stop. So the z cubes will cancel, and we're left with az squared minus 4z squared, which we factorize to get a plus 4, all multiplied by z squared. And we're left with bz plus 13z, which we factorize, so we have b minus 13 all times z. Now be very careful here with your signs, because technically in order to cancel out the z cubed, you're changing the sign, so it'd be z cubed minus z cubed equals 0, which means you're changing the sign of the minus 4z squared to be positive, and you're changing the sign of the positive 13z to be minus. And then we bring down our minus 65. So then we repeat the process. So a plus 4z squared divided by z squared leaves us with a plus 4. So now we're going to multiply a plus 4 by z squared minus 4z plus 13. So a plus 4 times z squared minus 4z plus 13 will be z squared times a plus 4 minus 4z times a plus 4 plus 13 times a plus 4. And by multiplying it out specifically in that way, it means that we have a plus 4z squared, which is what we want so that we can cancel these. So we're left with all of this equal to 0. And we're going to use this in the next part. So we're left with b minus 13z and minus 4 times a plus 4z. And we're going to put like to like. And likewise, we're left with minus 65 and 13 times a plus 4. And again, we'll put like to like. So we'll have 13 times a plus 4 equals minus 65. Minus 65 divided by 13 is minus 5. And minus 5 minus 4 is minus 9. So we're left with a is equal to minus 9. Next, we put our coefficients of z together. So we have b minus 13 is equal to minus 4 times a plus 4. And then we solve for b. We know that a is minus 9. So we have minus 9 plus 4, which is minus 5. And minus 4 multiplied by minus 5 is 20. So we have b minus 13 equals 20, and then 20 plus 13 is 33, so b is equal to 33. So the other factor we know is z plus a plus 4, and now we've figured out what the a is. We know it's minus 9, so the other factor is now z plus minus 9 plus 4, and minus 9 plus 4 is 5, so the other factor is z minus 5. And putting this equal to 0, the third root is z equals 5. Because z minus 5 equals 0, so z is equal to 5. Alternatively, by observing the first term z cubed and the last term minus 65, so z cubed and minus 65 in the cubic, we can see that the other factor has to be z minus 5, because 13 minus 5 is minus 65. And we know from the previous slide that z squared minus 4z plus 13 was one of the factors. So 13 times what gives us minus 65? Well, 13 times minus 5 gives us minus 65. Thus, z cubed plus az squared plus bz minus 65 is equal to z squared minus 4z plus 13, which is our factor, multiplied by z minus 5, which is the factor we just came up with. Multiplying out the brackets, z squared by z is z cubed, z squared by minus 5 is minus 5z squared, minus 4z by z is minus 4z squared, minus 4z by minus 5 is plus 20z, 13 by z is 13z, and 13 by minus 5 is minus 65. Simplifying, we bring down the z cubed, minus 5z squared minus 4z squared is minus 9z squared, 20z plus 13z is 33z, we bring down to 65. Hence, putting like to like, a is equal to minus 9, because obviously we had the a stuck onto the z squared. So if az squared is equal to minus 9z squared, then a is equal to 9. And b is equal to 33, because bz is equal to 33z, so b is equal to 33. The third root is given by z minus 5 equals 0, so z is equal to 5.